Tonight, imagine that every remaining second of your life has been converted into distance. An 80-year clock glows softly on the wall of a spacecraft. It does not count the years you have already lived. It begins now, at the moment the engines ignite. 8 decades are waiting inside those numbers. Nearly 1 billion heartbeats. Enough time for a child to become old, for cities to rise and change, for entire generations to pass through the world below. The ship lifts away from Earth. The moon is crossed in days. Mars can be reached in months under favourable conditions. Jupiter, Saturn, Uranus and Neptune each arrive as another boundary surrendered to motion. Behind you, the sun slowly loses its size. Its warmth becomes memory. The planets flatten into a thin, distant arrangement of lights. And yet, the nearest star has barely moved closer. The problem is not that the spacecraft has failed. The problem is that the scale has changed. Inside the solar system, distances are usually measured in astronomical units. 1 astronomical unit, or AU, is the average distance between Earth and the Sun, about 150 million kilometers. Neptune orbits roughly 30 AU from the Sun. Pluto spends much of its long path between about 30 and 50 AU. These are enormous distances by any human standard, but they remain small enough for sunlight to cross them in hours. The next star is not hundreds of AU away. Proxima Centauri is about 4.24 light-years from us, or roughly 268,000 AU from the Sun. Before we continue, if you enjoy calm journeys through the deepest questions in science, you can subscribe and return whenever you need another one. Light itself, moving almost 300,000 kilometers every second, needs more than 4 years to reach Proxima Centauri. That single comparison breaks the familiar map. Imagine shrinking the distance from the Sun to Earth until it measures 1 centimeter. Neptune would lie about 30 centimeters away. The planetary system could fit across a tabletop. Proxima Centauri, however, would not be sitting at the far end of the table. It would be almost 3 kilometers away. The planets are neighbors. The stars are another geography. Our most distant emissary, Voyager-1, began its journey in 1977. After visiting Jupiter and Saturn, it continued outward, eventually passing beyond the heliosphere, the enormous bubble shaped by the solar wind. In 2012, it became the first human-made object known to enter interstellar space. That sounds like the beginning of a voyage between stars. In one sense, it is. Voyager now travels through material no longer dominated by the outward flow of particles from the Sun. But crossing into interstellar space is not the same as reaching another star, and it may not even mean leaving every region that belongs to the solar system. Voyager moves at about 17 kilometers per second relative to the Sun. At that speed, it covers roughly 3.5 astronomical units each year. Give it the full 80 years on our imaginary clock, and it would travel only around 287 AU. Only is a dangerous word here. 287 AU is almost beyond ordinary imagination. It is approximately 43 billion kilometers. A radio message travelling at light speed would take nearly 40 hours to cross it. Such a voyage would carry a spacecraft far beyond every planet, beyond the familiar Kuiper belt, and deep into a darkness where the Sun would resemble an exceptionally bright star. Yet Proxima Centauri would still be almost 268,000 AU away. After an entire human lifetime, the nearest star would remain roughly 900 times farther than the distance crossed. This is the first honest answer to our question. With a speed similar to the one humanity has already sustained on an outward trajectory, a lifetime does not buy another solar system. It buys a thin extension of our reach into the outer domain of our own Sun. And even that description needs care. Far beyond Neptune may lie the Oort cloud, a vast, roughly spherical reservoir of icy bodies whose main region may begin several thousand AU away. Its outer population may extend tens of thousands of AU, perhaps toward 100,000. The boundaries remain uncertain, because the cloud has never been directly mapped. Its existence is inferred from long-period comets that fall inward from immense distances. Voyager may require about 3 centuries merely to enter the cloud, and perhaps 30,000 years to pass beyond its outer edge. So our spacecraft could cross the planets, pass through the heliosphere, enter interstellar space, and continue for 80 years without fully escaping the immense architecture associated with the star that launched it. That is difficult to feel, because maps make motion look easy. A line is drawn from one point to another. The spacecraft becomes a dot sliding across the page. Nothing on the map shows the decades occurring between 2 neighboring pixels. Nothing shows machines aging in vacuum, electrical power fading, surfaces being struck by particles, instruments losing sensitivity, or radio signals weakening as they spread across larger and larger spheres. A map compresses distance. A lifetime cannot. There is also a deeper problem hidden inside the word explore. If a spacecraft spends 80 years moving through mostly empty space, has it explored everything it crossed? It may measure magnetic fields, particles, dust, and radiation along the way. Those observations can transform science. Voyager has shown that apparently empty space contains structure, weather, boundaries, and history. But traveling through a region is not the same as arriving at a world. To explore a destination, a craft must reach the correct place. It must still be operating when it arrives. Its instruments must point in the right direction. It may need to slow down, enter orbit, survive local hazards, compare observations over time, and send what it learns across the darkness to someone capable of receiving it. Every one of those requirements consumes part of the lifetime. Acceleration consumes time. Braking consumes time. Observation consumes time. Communication consumes time. A return journey consumes the most time of all. The simple equation, speed multiplied by 80 years, therefore gives us the largest possible line the spacecraft could draw. It does not tell us how much of that line could be investigated, understood, or brought back into human knowledge. Our glowing clock has revealed only the first boundary. At present-day interstellar cruising speed, 80 years carries us hundreds of astronomical units. That is far enough to leave the planets behind and watch the sun become a point. It is far enough to enter an environment no human being has seen directly. It may be far enough to discover that the outer solar system is stranger than our models predicted. But it is not far enough to reach the nearest star. And before we can ask how to travel faster, we must solve a quieter problem. Where exactly does the solar system end? There is no single edge. The solar system ends differently depending on what exactly we are measuring. If the question concerns planets, the familiar system seems to fade somewhere beyond Neptune. If it concerns the particles and magnetic fields carried outward by the sun, the boundary lies much farther away. If it concerns objects held by the sun's gravity, the system may continue across a substantial fraction of the distance to the nearest star. These boundaries do not overlap neatly. A spacecraft can cross one while remaining thousands of years from another. The first boundary begins with the solar wind. The sun is not merely a glowing sphere surrounded by empty space. Its outer atmosphere continually releases electrically charged particles. Electrons and atomic nuclei stream away from the solar surface, carrying magnetic fields with them. Near Earth, this solar wind can disturb satellites, trigger auroras, and compress the planet's magnetic environment. Farther out, it continues past Mars, Jupiter, Saturn, and the final major planets. For a time, the wind moves faster than disturbances can travel backward through it. Information about conditions ahead cannot easily return toward the sun through the flow. But as the particles expand across a larger volume, they become thinner and eventually begin to encounter the material between the stars. That interstellar material is sparse, but it is not absent. It has pressure, motion, particles, and magnetic structure of its own. The first major change occurs at the termination shock. Here, the solar wind slows abruptly from supersonic to subsonic speed relative to the waves travelling through it. It has not stopped. It has not yet reached interstellar space. It has entered a broad, disturbed region where the outward flow from the Sun is being compressed and redirected by the surrounding galactic environment. This region is called the heliosheath. It is not a rigid shell. Its shape changes. The Sun moves through the local interstellar medium, while the strength of the solar wind rises and falls with solar activity. Conditions differ depending on direction. The boundary can breathe outward and inward rather than remaining at one fixed distance. Voyager 1 and Voyager 2 confirmed this unevenness by crossing the outer regions along different paths. Voyager 1 passed the termination shock farther from the Sun than Voyager 2. The bubble around the Sun was not the simple symmetrical sphere early diagrams often suggested. Beyond the heliosheath lies the heliopause. At this boundary, the outward pressure of the solar wind can no longer maintain control against the interstellar environment. Solar particles do not suddenly disappear, and interstellar particles do not begin at a perfectly clean wall. The transition is physically complicated. Particles can leak across, magnetic fields interact. The region immediately beyond may still be disturbed by the presence of the heliosphere. Yet the heliopause gives us one of the clearest operational definitions available. Cross it, and a spacecraft has entered interstellar space. Voyager 1 crossed this boundary in August 2012. Voyager 2 followed in November 2018. Their instruments detected changes in plasma, particle populations, and magnetic conditions that showed the probes had left the bubble dominated by the solar wind. The two crossings occurred at roughly 120 AU from the Sun, although in different directions and under different solar conditions. That distance is about 4 times Neptune's average distance from the Sun. It is also less than 1/2000th of the distance to Proxima Centauri. The word interstellar therefore creates a misleading emotional impression. It sounds as though Voyager has begun crossing the gap between complete star systems. Physically, the spacecraft is surrounded by material belonging to the space between stars. Geographically, it remains extremely close to the Sun compared with the distances separating one stellar system from another. A person stepping off a beach and entering the ocean has undeniably reached seawater. That does not mean the person has crossed the ocean. Even this comparison has limits. Because the heliopause is not a coastline, it is a changing balance between flows, fields, and pressures. But it clarifies the scale. Voyager has entered the medium between stars without coming close to another star. If we define the solar system by the heliosphere, then Voyager has left it. If we define the solar system by the Sun's orbiting population, Voyager is still deep inside. Far beyond the heliopause, the Sun may possess the Oort cloud. No spacecraft has seen it directly. Its existence is inferred mainly from the paths of long-period comets, which sometimes fall inward from immense distances and develop glowing atmospheres as they approach the Sun. The cloud is expected to be roughly spherical rather than arranged in a relatively flat disk like the planets. That shape preserves a history. The planets formed inside a rotating disk of gas and dust around the young Sun. Small, icy bodies were scattered outward by encounters with the giant planets. Some escaped completely. Others were thrown into extremely distant orbits, where passing stars and the gravitational influence of the Milky Way gradually altered their directions. Over immense spans of time, the original flattened distribution may have become a broad shell surrounding the planetary system. Current estimates commonly place the inner edge of the main cloud between roughly 2,000 and 5,000 AU, though more extended inner structures may begin closer. Its outer edge may lie anywhere from about 10,000 to 100,000 AU. At 5,000 AU, sunlight requires nearly a month to arrive. At 100,000 AU, the distance is more than 1.5 light years. The outer cloud may therefore reach a meaningful fraction of the way toward Proxima Centauri. At its farthest extent, the distinction between an object securely belonging to the Sun and one vulnerable to removal by another star becomes less definite. Gravity does not simply switch off at a boundary. The Sun's pull weakens with distance, but it never becomes exactly zero. Earth feels the gravity of the Sun, the Moon, Jupiter, nearby stars, and the galaxy simultaneously. What changes is which influence dominates the motion over long periods. Near the planets, the Sun's control is overwhelming. Far inside the Oort cloud, a small body may still orbit the Sun, but its path can be disturbed by the galaxy or by stars passing within a few light years. Near the outer edge, the idea of a clean gravitational border becomes increasingly artificial. One star's distant territory fades into the gravitational landscape of others. This gives our 80-year journey a more sobering scale. At a Voyager-like speed, the spacecraft would require roughly 3 centuries to reach even the estimated inner region of the Oort cloud. Passing through the entire cloud could take around 30,000 years. By then, recorded human history would fit several times inside the duration of the voyage. The craft would cross the heliopause early in the journey. It would spend nearly all the remaining time traveling through interstellar space, while still moving among objects that may belong to the Sun. This is not a contradiction. The heliosphere describes the reach of the solar wind. The Oort cloud describes a possible population of distant orbiting bodies. Gravitational dominance describes another, less distinct boundary. Each definition answers a different physical question. That is why a statement such as Voyager has left the solar system can be both useful and incomplete. It has left the Sun's plasma bubble. It has not crossed the full region occupied by objects gravitationally associated with the Sun. It has entered interstellar space without reaching another stellar system. A boundary that seemed like the end has become the beginning of a much larger outer country. The planets occupy only its bright central district. Beyond them lies the Kuiper belt. Beyond that, the heliosphere broadens and weakens. Outside the heliopause, interstellar particles flow around a spacecraft still traveling through the Sun's distant gravitational territory. Farther still, unseen comets may spend millions of years completing a single orbit. Our original question has therefore changed slightly. We are no longer asking only how far a spacecraft can travel during a life. We must ask which boundary it is capable of crossing, what that crossing physically means, and whether anything of scientific value can still be operating when it arrives. Present technology has already carried machines across the first great boundary. That achievement is real. Voyager has measured a region that no instrument before it could directly examine. But traveling farther requires us to avoid an easy mistake. We cannot take the highest speed ever displayed by any spacecraft, multiply it by 80 years, and call the result our exploration range. A record speed may last only briefly. It may be produced while falling toward the Sun. It may point in the wrong direction. It may belong to a trajectory that will never escape. To discover what present technology can honestly buy during one lifetime, we need a speed that a spacecraft can carry outward into the dark. The speed we need is not the speed a spacecraft reaches for a moment. It is the speed that remains after the launch vehicle is gone, the planetary encounters are over, and the Sun is shrinking behind it. That distinction gives us a practical benchmark. Voyager 1 is escaping the Sun at about 3.5 astronomical units per year. Voyager 2 is leaving slightly more slowly. These are not laboratory projections or unpublished engine concepts. They are measured outward motions carried by machines that have already crossed the heliopause and continued operating in interstellar space. Their motion was not produced by one miraculous engine burning continuously for decades. Most of the decisive work happened near the beginning. A launch vehicle lifted each probe away from Earth, then gravity assists at the giant planets changed the spacecraft's velocity relative to the Sun. During a gravity assist, a probe falls into a moving planet's gravitational field, curves around it, and departs with its path and solar velocity altered. The planet gives up an immeasurably small portion of its own orbital energy, while the lightweight spacecraft gains a useful amount. After the final encounter, the probe does not need to keep pushing in order to preserve its motion. In the near vacuum of deep space, there is no atmospheric drag steadily bringing it to a halt. The Sun continues to pull backward, so the outward speed changes, but a spacecraft placed on an escape trajectory will not turn around and fall home. This is what makes Voyager valuable as a measure of demonstrated reach. It represents an entire working chain: launch, navigation, planetary assistance, long-duration power, communication, autonomous fault protection, and a trajectory that genuinely continues outward. Now give that motion our full 80-year clock. At roughly 3.5 AU per year, Voyager 1 would add about 287 AU. That is less than 5,000ths of a light year. The calculation assumes the spacecraft begins the lifetime already moving at its mature outward rate, so it is more generous than a mission that must first launch from Earth and acquire that velocity. The result remains enormous in human units. A radio transmission would need almost 40 hours to cross the distance. The sun's light would be so weak there that a square meter facing it would receive less than 100,000th of the solar energy reaching the same area near Earth. Yet if the spacecraft began beside the sun, 80 years of Voyager-like motion would carry it only around 1/900th of the way to Proxima Centauri. The nearest stellar system would not become the next destination. It would remain almost the entire journey away. New Horizons is also escaping the solar system after its encounter with Pluto and the distant object Arakoth, along with the 2 Voyagers and the 2 Pioneer spacecraft. It belongs to a very small set of human-made objects on outward trajectories that would carry them into interstellar space. Together, they reveal something important about the phrase current technology. There is no fleet of vehicles steadily accelerating into the galaxy. There are a few small robotic craft following carefully designed escape paths, most of them launched before modern smartphones, fiber optic networks, or the commercial internet existed. Their distance comes less from violent continuous propulsion than from patience. That patience is powerful. A machine moving only a few astronomical units per year can cross boundaries no human has visited and sample material that has never entered an Earth laboratory. It can turn the almost empty region beyond the planets into a place with measurable particle densities, magnetic fields, plasma waves, and cosmic rays. But patience cannot convert hundreds of AU into light years within a human lifespan. Nor can we simply scale Voyager into a crude ship. Voyager 1 launched with a mass roughly comparable to a small car. It does not carry air, water, food, living space, radiation shelters, medical systems, replacement machinery, or a propulsion system able to brake at a destination. Its radioisotope power source gradually weakens. Its transmissions spread across space and arrive at Earth extremely faint. Engineers can conserve power, reconfigure systems, and extend operations, but no spacecraft is immune to aging. A vehicle carrying people would be much heavier. Increasing mass does not change the laws of motion, but it changes the size of the launch system, the amount of propellant, and the energy required to reach the same velocity. A life support habitat also creates more components that can fail during decades when rescue and replacement are impossible. So the 287 AU figure is not the distance a human crew can presently be expected to explore. It is a generous geometric ceiling based on one of the best outward cruise speeds humanity has actually demonstrated with a robotic probe. The scientific range would be smaller still. A spacecraft can continue moving after its power falls below the level needed for instruments and communication. It may physically reach a region without being capable of examining it. Its antenna may no longer point accurately. Its transmitters may become too weak. Its instruments may fail one by one. Motion can survive after the mission has ended. This creates 2 separate frontiers. The first is the material frontier, the farthest distance traveled by an object we built. The second is the living frontier of exploration, the farthest place from which a functioning machine can gather evidence and return it to human beings. The first frontier can drift outward silently for millions of years. A dead spacecraft remains a spacecraft. Its trajectory does not require its computer to be awake. The second frontier must be continuously maintained. Power must reach the electronics. Thermal conditions must remain survivable. The craft must know its orientation. Commands must cross the growing delay. Data must be encoded, transmitted, detected, corrected, and understood. At hundreds of AU, a small repair cannot be performed by a visiting crew. Every recovery must come from software, redundant hardware, or an engineering possibility designed into the machine decades earlier. Voyager 1 still communicates with Earth, although by 2026, only its magnetometer and plasma wave instrument remained active. Its exploration frontier is being maintained by a shrinking power supply and an engineering team continually choosing which parts of the spacecraft must fall silent next. That makes its achievement more meaningful than a distance record alone. The machine has continued returning measurements from beyond the heliopause, while almost every original system has aged into silence. Still, demonstrated outward technology leaves the title's first answer almost painfully local. In one lifetime, a robotic craft can travel far beyond the planets. It can cross the sun's plasma boundary. It can examine a portion of the interstellar medium and push human measurements several hundred AU into the dark. It cannot reach another star. Even the most optimistic multiplication of an already achieved escape speed leaves the next stellar system about 900 times too far away. This conclusion seems to invite an obvious objection. Voyager is not the fastest spacecraft humanity has built. Parker Solar Probe has moved through the Sun's outer atmosphere at about 430,000 miles per hour, more than 10 times Voyager 1's outward speed, and faster than any other human-made object. Multiply that number by 80 years, and the answer appears to change. But Parker's record does not belong to a ship racing outward toward another star. It belongs to a spacecraft falling around the Sun. During its closest approaches, Parker Solar Probe moves at nearly 700,000 kilometers per hour. The record was reached during its passage on December 24, 2024, when the spacecraft came within about 3.8 million miles of the solar surface, and Parker has matched that speed during later encounters. If that number could be pointed toward Proxima Centauri and maintained for 80 years, the result would appear impressive. Parker would cover a little more than 3,000 AU, or slightly above 5/100ths of a light year. That would be more than 10 times the distance produced by a Voyager-like cruise. It would also leave the nearest star more than 80 times farther away. Even this imaginary calculation, generous beyond anything Parker was designed to do, fails to purchase another solar system. More importantly, it treats the spacecraft's highest instantaneous speed as though it were a permanent outward velocity. It is not. Parker follows a deeply elongated orbit around the Sun. It dives inward, races through the lowest part of that orbit, then climbs outward and slows. The spacecraft remains gravitationally bound. Its path carries it back for another close encounter, rather than releasing it into the space between stars. The mechanism begins with a difficulty that sounds backwards. Reaching the outer solar system requires a spacecraft to gain enough energy to climb away from the Sun. Reaching the Sun requires it to lose much of the sideways motion it already possesses. Earth travels around the Sun at almost 30 kilometers per second. A spacecraft launched from Earth begins with nearly the same solar orbital motion. Pointing a rocket inward does not make that sideways velocity disappear. Without reducing it substantially, the vehicle continues to miss the Sun and orbit around it. Parker therefore used repeated encounters with Venus to change its orbit. During each flyby, the planet's gravity altered the spacecraft's direction and reduced its speed relative to the Sun, allowing the closest point of the next orbit to fall deeper into the solar gravitational field. This is an unusual gravity assist because the mission is not primarily trying to leave the solar system faster. It is using a moving planet to surrender orbital energy. Once Parker begins falling deeper, the Sun performs the dramatic part. Gravitational potential energy becomes kinetic energy. The spacecraft accelerates as its distance from the Sun decreases. Near perihelion, the closest point in its orbit, its speed reaches the record value. Nothing has pushed Parker continuously to 430,000 miles per hour. Much of that velocity comes from falling through the Sun's gravitational field. After the close passage, the process reverses. The spacecraft climbs outward. Kinetic energy becomes gravitational potential energy again. Parker slows as it moves away from the Sun. Just as an object thrown upward from Earth slows while climbing, Its record speed belongs to a particular region of its orbit, not to the entire path. Parker is never falling straight down, and there is no solid valley surrounding the Sun. It is moving sideways rapidly enough to keep missing the star. Still, the image reveals the trap. An object can become extraordinarily fast at the bottom of a gravitational well without carrying that full speed away from the well. This is why speed records require a reference frame and a mission context. A spacecraft can be measured relative to Earth, the Sun, a planet, or the local center of mass. The numerical result changes because each reference object is moving. For interstellar travel, the most useful question is not simply how fast the vehicle becomes near the Sun. It is how much outward speed remains when the craft is far away and the Sun's gravitational pull has weakened. Engineers sometimes describe this remaining motion through hyperbolic excess velocity, the speed a departing spacecraft would still possess after escaping the central body's gravitational influence. A probe may have a spectacular speed at perihelion and almost no interstellar excess speed if its orbit remains closed. It has no escape speed at all in the practical sense. It will continue returning. Parker's record is therefore not exaggerated. It is exactly the speed required by the scientific mission. The probe was built to sample the solar corona, investigate the origin of the solar wind, and measure fields and particles close to the region where they are produced. High velocity near the Sun allows the spacecraft to survive a brief, carefully controlled encounter, while its heat shield protects the instruments behind it. The mission's value comes from approaching the Sun, not from escaping it. Using Parker as an interstellar benchmark would be like measuring how far a stone can leave a planet by recording its speed just before it reaches the ground. The number is real. The direction and energy state are wrong. There is, however, a reason mission designers remain interested in traveling close to the Sun. If a spacecraft could perform a powerful engine burn while moving rapidly near perihelion, the burn could produce a larger change in its final escape energy than the same burn performed farther away. This is known as the O-berth effect. Solar gravity could help a craft gain enormous speed before propulsion adds another carefully directed increase. The idea suggests possible routes toward faster interstellar probes. It also creates severe engineering demands. A vehicle must first lose enough orbital energy to fall close to the Sun. It must survive intense heat and radiation. Its propulsion system must operate at precisely the right moment. The resulting trajectory must point toward the intended star. The craft must then retain useful instruments, power, communication equipment, shielding, and perhaps some way to slow down decades later. Parker demonstrates that a lightweight robotic spacecraft can survive repeated passages extraordinarily close to the Sun. It does not demonstrate an engine capable of taking a large exploration vehicle through perihelion and launching it toward another star at Parker's record speed. The distinction becomes even sharper when humans are added. A heat shield protects Parker because the spacecraft can keep the shield pointed toward the Sun while most of its vulnerable systems remain in shadow. A crewed interstellar vehicle would need far more mass, internal volume, life support, radiation protection, redundant machinery, and long-term cooling. Every kilogram added for survival must be accelerated. Every additional meter of shielding changes the propulsion problem, and every increase in outward velocity must eventually be removed if the mission intends to stop. The fastest measured spacecraft therefore does not give us the greatest explorable distance. Parker and Voyager answer different questions. Parker tells us how fast a small machine can move while deep inside the Sun's gravity. Voyager tells us how much outward velocity a spacecraft can carry into interstellar space after its major encounters are complete. Neither reaches even 1/1000th of light speed. Parker's record is roughly 0.06% of the speed of light. Voyager's outward motion is smaller still. The gap between these machines and a practical interstellar craft is not a modest improvement waiting for a better engine. It spans several orders of magnitude, along with entirely new problems in energy, shielding, navigation, reliability, and braking. So the next useful calculation cannot begin with another speed record. It must begin with fractions of light speed. At 1%, the geography changes. At 10%, nearby stars begin to enter a human lifetime. At 20%, the number of possible destinations grows again. But each larger circle on the map conceals a cost that simple multiplication has not yet revealed. The first fraction sounds almost modest. 1% of the speed of light is about 3,000 kilometers per second. That is more than 170 times Voyager 1's outward speed. It is fast enough to circle Earth in roughly 13 seconds. A spacecraft moving at that velocity could cross the average distance between Earth and the Moon in a little over 2 minutes. Yet on the scale between stars, 1% of light speed is still slow. During an 80-year lifetime, a craft moving continuously at that velocity would travel 0.8 light-year. It would cross almost 51,000 astronomical units, carrying it far beyond the planets and deep into the possible region of the Oort cloud. It would not reach Proxima Centauri. At 10% of light speed, the picture changes. Maintain that velocity for 80 years, and the spacecraft draws a line 8 light-years long. For the first time, more than one stellar system enters the mathematical range of a single human lifetime. Alpha Centauri lies inside it. Barnard's star lies inside it. Several other nearby stars begin to appear on the map. At 20% of light speed, the line reaches 16 light-years. At half the speed of light, it reaches 40. At 90%, it reaches 72. There is a simple rule hidden inside those numbers. For any speed below light, the ideal 80-year reach is 80 multiplied by that fraction of light speed. 10% gives 8 light-years. 20% gives 16. Every real mission requirement can only subtract from that ceiling. The calculation has quietly removed the mission. It assumes the spacecraft begins at full cruise speed at the first second of the journey. There is no launch, no acceleration, no time spent leaving the solar system, and no period during which the vehicle gradually approaches its intended velocity. At the end of 80 years, it does not slow down. It does not enter orbit. It does not turn toward a planet, deploy a lander, or remain long enough to observe a changing atmosphere. The final second of the traveler's life arrives while the ship is still passing through the destination at full speed. The result is not an exploration radius. It is the maximum length of an ideal straight line. Acceleration begins to shorten it. Suppose a future ship could provide a comfortable acceleration similar to gravity on Earth. That would be an extraordinary capability, far beyond any propulsion system now available for interstellar travel. Even then, reaching a large fraction of light speed would require sustained thrust and immense energy. The destination creates the second half of the problem. A spacecraft arriving at 20% of light speed does not arrive in the ordinary sense. It crosses the target system at 20% of light speed unless some mechanism removes that velocity. To stop, the ship must lose nearly the same amount of motion it worked so hard to gain. A conventional design might turn around and fire its engines in the opposite direction, but the braking propellant had to be carried through the entire first half of the journey. The craft accelerated the fuel that would later decelerate it. More fuel required more fuel to accelerate that fuel, causing the initial mass to grow rapidly. A round trip contracts the range further. At 10% of light speed, 80 years of uninterrupted motion equals 8 light-years. But a traveller who must return to Earth can spend only half that distance moving outward. The theoretical turning point becomes 4 light-years away, even before time is reserved for acceleration, braking, or exploration. Proxima Centauri lies about 4.24 light-years from the Sun. At 10% of light speed, an ideal craft could not quite reach it and return within 80 years, even if it turned around immediately and ignored every period spent changing velocity. At 20% of light speed, the simple round-trip radius becomes 8 light-years. Alpha Centauri fits inside the geometry, but the word comfortably applies only to the arithmetic. The spacecraft still needs to accelerate, brake, survive, investigate, depart, accelerate again and brake near Earth. Information creates another limit. A robotic probe does not need to bring its instruments home if it can transmit the results. But the signal cannot travel faster than light. For a probe moving at a fraction called beta of light speed, the furthest destination whose first signal can return within 80 Earth years is 80 beta divided by 1 plus beta. At 1% of light speed, that distance is about 0.79 light year. At 10%, it is about 7.3 light years. At 20%, about 13.3. At half light speed, about 26.7. At 90%, about 37.9. These are not 5 answers to one question. They are answers produced by different definitions of exploration. A probe may reach farther than the distance from which its discoveries can return during the same human lifetime. The speed ladder remains valuable because it shows where the interstellar threshold begins. At 1% of light speed, an 80-year mission remains inside the Sun's wider neighborhood. At 10%, the nearest stars become physically reachable. At 20%, a larger local population enters the mathematical range. But none of these percentages should be treated as a promise. The larger the percentage becomes, the more the answer depends on everything except the multiplication that produced the number. So the next step is not to draw a larger circle around the Sun. It is to choose a real destination and force every hidden requirement into the same calculation. The nearest stellar system gives us the fairest possible test. It is closer than every other star. It offers multiple stars, possible planets, and extraordinary scientific value. If interstellar exploration can fit inside one human lifetime anywhere, Alpha Centauri should be the easiest place to prove it. Alpha Centauri is not a single star waiting alone in the dark. It is a system of 3. Alpha Centauri A and Alpha Centauri B are Sun-like stars orbiting one another. Farther from that pair lies Proxima Centauri, a small red dwarf and the closest known star to our Sun. Proxima is about 4.24 light-years away. The brighter pair lies slightly farther, at roughly 4.37 light-years. The difference between those distances is small enough to disappear on most maps. For a spacecraft, it can represent months or years. Proxima is the obvious first test because it is the closest. It also has known planets, including Proxima b, a rocky world orbiting close to its star. Whether that world possesses an atmosphere or conditions suitable for life remains unresolved, especially because Proxima produces energetic flares. Yet even an airless or hostile planet would be scientifically valuable. It would be the first world examined from inside another stellar system, rather than through a telescope near Earth. The destination is therefore real. The journey is where the definitions begin to separate. At Voyager 1's outward speed, a trip across 4.24 light-years would require roughly 75,000 years. A probe launched when humans first began recording history would still have most of the voyage ahead of it. 1% of light speed changes the unit of disappointment. Instead of 75,000 years, the crossing requires about 424 years. That is short enough to imagine as a project maintained by a civilization, but far too long to fit inside one ordinary life. The people who build the machine would never see it arrive. Their grandchildren would not see it arrive. Several additional generations would be born and die while the probe continued through the space between the stars. At 10% of light speed, the calculation finally enters a human timescale. Proxima could be reached in about 42 years if the spacecraft acquired its cruise velocity immediately and never slowed down. A probe launched near the beginning of a scientist's career might arrive while that scientist was still alive. But Earth would not know that it had arrived. The first signal would require another 4.24 years to cross the distance home. The earliest evidence from the encounter would therefore reach Earth roughly 46 or 47 years after launch. That still fits inside an 80-year clock. So at 10% of light speed, Alpha Centauri appears to pass our first meaningful test. A machine could reach the nearest star, collect something, and return information within one human lifetime. Only one word remains dangerously undefined: collect. A probe moving at 10% of light speed crosses 1 astronomical unit in about 83 minutes. The scale of a planetary system is enormous, but the spacecraft's speed has become enormous as well. A camera approaching Proxima b would see the target grow from an unresolved point into a world, sweep through its closest observing geometry, and begin receding again within a narrow period. Years of anticipation would compress into hours of useful proximity. At 20% of light speed, the journey falls to a little over 21 years. Add the returning light time, and the first results could arrive around 25.5 years after departure. That is the basic premise behind Breakthrough Starshot, a research and engineering effort examining whether ultralight, uncrewed sailcraft might be accelerated by a powerful beam toward roughly 20% of light speed and sent on a flyby of Alpha Centauri. The concept concerns gram-scale machines, not crewed ships, and remains a proof-of-concept effort, with major engineering challenges unresolved. At that speed, 1 astronomical unit passes in about 42 minutes. The distance from Earth to the Moon would be crossed in a little over 6 seconds. For 2 decades, the target would remain little more than a carefully tracked point. Then, during the final approach, the point would become a system. Instruments that had waited through billions of silent kilometers would suddenly face their entire scientific mission compressed into a few hours. The probe would not have time to circle a planet, wait for weather to change, compare seasons, or return to a feature that appeared unusual. Its instruments would need to identify targets, adjust exposure, stabilize images, measure particles and fields, store data, and survive the encounter while the entire geometry changed from minute to minute. Accuracy would have to begin decades before arrival. A tiny error in launch direction would grow across more than 4 light years. The target would not remain fixed while the probe traveled. Proxima moves through space. Its planets continue around it. Mission planners would have to predict where the chosen world would be when the craft arrived, not where it appeared when the beam first accelerated the sail. The probe would also approach with limited opportunity for major correction. A gram-scale vehicle cannot carry a conventional engine. Large fuel tanks, a powerful computer, broad shielding, several telescopes, and a large radio dish. Miniaturization makes the speed conceivable by reducing the mass that must be accelerated. But the same reduction makes every scientific and engineering function more difficult. A large planetary probe can carry redundant systems. If one instrument fails, another may continue. It can possess several antennas, substantial power, thermal control, radiation protection, and enough propellant to adjust its orbit. An interstellar nanocraft would attempt to place sensing, processing, navigation, power, communication, and survival inside a mass measured in grams. The sail that helped accelerate it might later become part of the communication system. The probe would need to return its discoveries across more than 4 light years, using an extremely limited energy supply. The downlink would be photon-starved, technically demanding, and dependent on large receiving systems near Earth. The data would not arrive all at once. Images and measurements might be transmitted slowly over months or years. Some packets could be lost. A failure after the flyby could erase observations gathered during the only close encounter the craft would ever receive. Sending a fleet rather than one probe could reduce that risk. Multiple sailcraft could observe from different trajectories, replace failed units, and perhaps relay or combine information. Yet even a successful fleet would remain a flyby mission. It would not stop. It would not become an artificial moon of Proxima b. It would not descend through an atmosphere, touch a surface, or remain beside the planet while conditions changed. After the brief encounter, every probe would continue outward into space. This does not make the mission scientifically empty. A well-designed flyby could measure a planet's size, color, reflectivity, possible atmospheric signatures, magnetic environment, surrounding dust, and perhaps large surface contrasts. It could transform Alpha Centauri from a remote set of points into a physical place. Humanity has learned enormous amounts from flybys before. The first close views of several planets and moons came from spacecraft that could not remain. But an interstellar flyby at 20% of light speed occupies an extreme edge of that category. Its years of travel are long. Its moment of proximity is short. Its communication channel is narrow. Its second chance does not exist. Alpha Centauri therefore answers one version of the title with surprising optimism. A sufficiently advanced robotic probe moving at 10 or 20% of light speed could reach the nearest star, return at least some information within one human lifetime. But it would explore in the thinnest practical sense, a rapid passage, a compressed sequence of measurements, and a signal sent backward from a machine already disappearing into deeper space. To remain, revisit, compare, and understand the system over time, the probe must surrender almost all the velocity that carried it there. The journey to Alpha Centauri is difficult. Stopping at Alpha Centauri may be harder. A spacecraft traveling at 20% of light speed carries an extraordinary amount of kinetic energy. That energy does not vanish when the destination appears. Unless some physical process removes it, the craft continues through the system at the same immense velocity that made the journey possible. Arrival is therefore not a location. It is a change in motion. To remain near Proxima Centauri, the probe must reduce its speed relative to the star from roughly 60,000 kilometers per second to something compatible with a stable orbit. That means surrendering almost all the velocity gained at departure. The requirement is easy to hide inside a mission diagram. A line leaves the Sun, crosses 4 light years, and ends beside another star. The endpoint creates the illusion of rest. In reality, the spacecraft would reach that point with enough momentum to cross the entire target system and disappear into interstellar space. A conventional solution would be to carry an engine and braking propellant. The spacecraft could rotate during the voyage, point its engines forward, and begin thrusting against its direction of travel. If the acceleration profile were carefully chosen, the craft might reach the destination with most of its relative velocity already removed. This sounds like the journey divided into 2 equal tasks. First accelerate, then decelerate. But the mass does not divide so neatly. The braking fuel must be accelerated during departure. The fuel used to accelerate that braking fuel must also be carried. This recursive burden is why the rocket equation turns high velocity into a rapidly expanding mass problem rather than a simple request for a larger tank. At ordinary mission speeds, engineers already treat this relationship with great care. For a chemical rocket leaving Earth, a large portion of the starting mass may be propellant. Reaching a significant fraction of light speed would push the problem into an entirely different regime. No existing chemical fuel contains enough usable energy per kilogram to make such a journey practical. Nuclear fission offers far greater energy density. Fusion could offer more. Antimatter, if it could be produced, stored, and controlled in useful quantities, would release still more energy through annihilation with matter. Yet high energy density does not automatically create an efficient engine. The energy must be converted into directed exhaust. The engine must survive the process. Waste heat must be removed. The exhaust velocity must be high enough to prevent the required mass ratio from becoming impossible. A powerful energy source attached to an inefficient propulsion system may still fail to move a useful payload across the stars. The braking phase repeats the demand. A craft that accelerates itself using onboard propellant must either save enough reaction mass for the destination or find another way to slow down. This is why some interstellar concepts separate the energy source from the spacecraft. A beam-driven sail does not carry the laser that accelerates it. The power remains near the solar system, while light pushes against a sail attached to an extremely small probe. Removing the onboard propulsion plant and most of the fuel can make very high velocity conceivable. But the same advantage becomes a weakness at Alpha Centauri. The laser array remains behind. Once the probe reaches the target, no equivalent beam is automatically waiting ahead to slow it down. The craft may attempt to use the destination itself. One proposed method is a magnetic sail. The spacecraft would deploy a large magnetic field that interacts with charged particles in the interstellar medium or the stellar wind. Those particles would be deflected, and the reaction could gradually reduce the craft's velocity. An electric sail follows a related idea using charged structures and electrostatic interaction. A light sail might also turn its surface toward the approaching star and use stellar radiation pressure for braking. In some proposals, the combined light of Alpha Centauri A and B could help slow a very lightweight sail before it continued toward Proxima. None of these methods behaves like pressing a brake pedal. The surrounding particle density is extremely low. Stellar light grows stronger only near the destination. The sail or magnetic structure may need to span an enormous area while remaining exceptionally light. It must deploy successfully after decades in space, maintain the correct orientation, survive impacts, and produce enough deceleration before the target system has already passed. The required braking distance may itself be measured in astronomical units, thousands of astronomical units, or more. A spacecraft cannot wait until it reaches the planet and then decide to stop. It must begin surrendering speed long before arrival. This creates a navigational commitment. If the probe starts braking toward the wrong trajectory, it may not possess enough remaining control to correct the mistake. The star's motion, the probe's approach angle, and the positions of any planets must be predicted with extraordinary precision. The faster the vehicle approaches, the earlier the decision must be made. Braking also changes the mission clock. A probe traveling at 20% of light speed can cross the distance to Proxima in a little over 21 years if it cruises at that speed for nearly the entire journey. A probe that spends a large portion of the voyage accelerating and decelerating cannot use the same calculation. Its average speed becomes lower, the arrival date moves farther into the future, the region reachable within one lifetime contracts. A flyby and an orbital mission may therefore begin with the same destination but require fundamentally different spacecraft. The flyby probe is rewarded for being small, fast, simple, and expendable. It may carry limited instruments, survive one close passage, transmit what it can, and continue outward forever. An orbital probe needs propulsion or a braking system, more power, stronger navigation, longer operational life, and greater protection. It must reach the destination with enough surviving capability to perform years of observations. A vehicle designed only to arrive quickly is optimized to preserve velocity. A vehicle designed to explore is optimized to destroy that velocity. Those are not small variations of the same mission. They are opposing spacecraft philosophies. Higher speed can reduce the amount of exploration accomplished at the destination. At 20% of light speed, a probe receives only a brief observing window. At 1%, the journey is far too long for one human lifetime. But the encounter would unfold more slowly. If the craft could brake completely, even a modest instrument package might study the system for years. The most useful mission is not automatically the one that arrives first. It is the one that reaches the target with the greatest surviving ability to answer the central scientific questions. For a crewed vehicle, braking becomes even more unforgiving. The ship cannot simply vanish into interstellar space after passing the destination. The people aboard require an orbit, a stable trajectory, or another controlled path. Their habitat, shielding, food systems, water recycling, medical equipment, and repair machinery increase the mass that must be slowed. Any failure during deceleration occurs after decades of travel, when replacement parts cannot arrive and Earth cannot intervene in real time. A braking engine must function after years of radiation, vibration, thermal cycling, and exposure to dust. If the mission depends on a sail, that sail must deploy correctly. If it depends on a target star's wind, the actual wind must behave closely enough to the model. If it depends on antimatter, fusion, or another advanced propulsion system, that system must remain reliable across the entire voyage. The journey's greatest mechanical event may occur at the moment when the spacecraft is oldest. Even successful braking is not the end. A probe that slows near Proxima still has to choose what to explore. It may need to move between planets, avoid flares, measure the stellar environment, search for moons, and enter orbit around a small world moving rapidly through a complex gravitational system. Each maneuver requires energy. Every kilogram of reserve propellant reduces the mass available for instruments, shielding, or communication. The mission must decide its priorities before departure, perhaps decades before the first close measurements reveal what the system actually contains. That is the hidden price of stopping. The spacecraft gains time at the destination by surrendering speed, payload, simplicity, and range. A fast probe can touch a distant system. A slow probe can remain. A heavily equipped probe may understand more, but it becomes harder to send. The word exploration now demands another correction. Reaching Alpha Centauri is not the conclusion of the mission. It is the point at which patient observation can finally begin. And meaningful observation requires something the speed calculations have barely allowed so far. Time spent going nowhere. Time spent going nowhere is the very thing that turns arrival into exploration. A spacecraft can cross a planetary system in hours. Understanding that system may require years. A single image can show the color of a world or the shape of a cloud. A sequence can show motion. Repeated observations can reveal seasons, weather, rotation, volcanic activity, changing ice, shifting dust, storms, auroras, and the movement of moons. Without time, a probe sees an event. With time, it begins to see a system. Humanity has already witnessed the difference. New Horizons spent more than 9 years traveling to Pluto. During the core encounter, it completed 236 scientific observations across roughly 30 hours. The spacecraft passed the world once, turned its antenna home, and then spent 15 months returning the complete dataset at only 1 or 2 kilobits per second. That programmed rush transformed Pluto. It revealed mountains of water ice, a vast nitrogen glacier, atmospheric haze, and a level of geological complexity that distant observations had not predicted. Cassini explored differently. It remained in the Saturn system for 13 years, completing 294 orbits. It returned 127 times to Titan and 23 times to Enceladus. It watched seasons change, followed storms, passed through plumes, mapped seas, and revisited the same worlds under new conditions. New Horizons revealed a world in a decisive glance. Cassini watched a planetary system become a changing place. The difference between reaching and exploring is the difference between an encounter and a relationship. An orbit creates a changing geometry between the probe, the target, its star, and Earth. Features hidden in darkness rotate into view. The same atmosphere can be examined at sunrise, midday, sunset, and night. Different wavelengths can reveal temperature, composition, clouds, surface minerals, magnetic fields, or escaping gases. One passage offers a profile. Many passages create a model. A flyby may reveal a cratered surface that appears inactive. Later observations may detect fresh deposits, temperature anomalies, moving plumes, or subtle changes between one pass and the next. A planet that looks uniform in a distant image may contain radically different regions once it is mapped at higher resolution. Every scientific question has a minimum observing time. To measure the size of a planet, one pass may be enough. To determine its rotation rate, the craft may need to watch identifiable features return. To detect seasons, it may need to remain through a meaningful fraction of the planet's orbit around its star. To understand weather, it must separate temporary conditions from persistent patterns. To search for life, it may need to distinguish a biological signal from geology, chemistry, contamination, or instrument error. Exploration is not merely collecting more data, it is creating enough independent evidence to reject the wrong explanations. Suppose a probe near Proxima b detects oxygen in an atmosphere. Oxygen can be associated with life on Earth, But oxygen alone would not prove life. Ultraviolet radiation can split water molecules. Hydrogen may escape to space, leaving oxygen behind. Surface minerals may react with atmospheric gases. The star's activity may drive unfamiliar chemistry. The probe would need context. How much water is present? What other gases accompany the oxygen? Does the atmosphere change with season? Is methane present far from chemical equilibrium? How active is the star? Does the planet possess a magnetic field? Are the signals global, regional, temporary, or stable? One measurement creates excitement. A network of related measurements creates an argument. The same standard applies even when life is not involved. To understand whether a planet is habitable, scientists need its atmosphere, pressure, temperature distribution, cloud behavior, surface composition, radiation environment, and the way heat moves from one region to another. A world orbiting a red dwarf may keep the same face directed toward its star. One hemisphere could remain under permanent daylight, while the other remains dark. But winds and oceans might transport heat. Clouds could form over the brightest region and reflect energy into space. Ice might accumulate on the night side. Atmospheric gases could freeze out if circulation is weak. A probe passing once cannot watch those processes settle into patterns. To explore the system deeply, the spacecraft must become patient. Patience creates engineering demands of its own. The probe needs a power source that can operate far from the sun. Solar panels may receive useful energy near a star, but the spacecraft must survive the interstellar approach before that light becomes strong. Batteries cannot sustain a mission lasting decades. Radioisotope systems provide long-lived power, but their output declines. Reactors may offer more energy while adding mass and complexity. Heat must be managed even in cold space. Electronics, instruments, computers, and transmitters generate waste heat. A spacecraft cannot cool itself through surrounding air. It must radiate energy away through dedicated surfaces. Large radiators add area and vulnerability. Near an active red dwarf, the thermal environment may also change during flares. Communication rewards time as well. A distant probe may need months or years to transmit a detailed archive. The farther it travels, the weaker its signal becomes when received on Earth. A high-resolution map or atmospheric spectrum contains vastly more information than a simple beacon announcing survival. The probe may collect data faster than it can send it. That creates choices. Which images are preserved at full resolution? Which discoveries deserve immediate transmission? What happens if the communication system fails before the archive is complete? An orbital mission can send information gradually. A high-speed flyby may gather its best data during a short encounter, then spend years transmitting from increasing distance. Autonomy becomes unavoidable. At Alpha Centauri, a command from Earth needs more than 4 years to arrive. The response needs more than 4 years to return. A simple question and answer exchange takes over 8 years. No controller can guide the craft through a sudden hazard in real time. The spacecraft must recognize problems, choose targets, alter priorities, protect instruments, and recover from faults without waiting for human permission. Its software must make decisions inside an environment never seen directly. A strange object may appear. A flare may threaten sensitive equipment. A moon may cross the field of view. The probe cannot ask Earth what to do and receive an answer before the opportunity has vanished. For a human crew, judgment travels with the mission. But the survival burden becomes far larger. People need systems that renew air and water. Food must be stored, grown, or manufactured. Waste must be processed. Microorganisms must remain controlled without destroying the useful ecosystems inside the habitat. Bones, muscles, immune systems, sleep, mental health and reproduction may all respond to years of confinement and altered gravity. Artificial gravity could reduce some risks, but producing it requires rotation or continuous acceleration. Rotation brings structural complications. Continuous acceleration demands propulsion and energy beyond present capability. The crew must also maintain machines that cannot be replaced from Earth. A failed pump cannot wait 8 years for advice. A damaged seal cannot be postponed until resupply. Every essential function needs redundancy, repair access, spare parts, and people able to understand unfamiliar failures. The longer the crew remains at the destination, the more scientific value the mission gains. The longer it remains, the more opportunities appear for something essential to break. A fast mission reduces exposure during the cruise, but allows little time to explore. A slow mission permits deeper investigation, but demands greater reliability, more power, more supplies, and longer biological survival. A settlement could remain indefinitely, but then the mission has abandoned the requirement to return. A round trip preserves the idea of coming home, but every year spent studying the destination must be removed from the time available for travel. The radius of exploration contracts with every honest demand. First, the craft must reach the star. Then it must slow down. Then it must remain functional. Then it must observe long enough to separate patterns from accidents. Then it must communicate enough evidence for people on Earth to understand what it found. And if humans travel aboard it, they must survive not only the motion through space, but the quiet years when the spacecraft is no longer moving toward the destination at all. By this definition, deeply exploring Alpha Centauri within one ordinary lifetime becomes far harder than merely crossing the distance. Yet one assumption has remained untouched through every calculation. The 80-year clock has always been imagined on Earth. Near the speeds required to make the larger universe accessible, that clock is no longer the only one that matters. The clock aboard the spacecraft does not agree. At ordinary speeds, the disagreement is too small to matter. A passenger on an aircraft, an astronaut orbiting Earth, and a person standing on the ground all experience slightly different amounts of elapsed time, but the differences are measured in fractions of a second. They can be detected with precise clocks. They do not transform a human life. Interstellar speed changes that. As a spacecraft approaches the speed of light, the time measured by the traveller can become dramatically shorter than the time measured by people who remain on Earth. This is not an illusion caused by a faulty clock. The traveller's clock is not running incorrectly. Their heartbeat, thoughts, chemical reactions, and biological aging continue at their usual local rates. Earth's clock is also functioning correctly. The two paths through space-time contain different amounts of elapsed time. That statement is difficult because everyday experience trains us to imagine time as a universal river. Events may happen at different places, but the same seconds seem to pass everywhere. A clock in London, a clock on Mars, and a clock moving between the stars appear to belong to one shared present, provided their mechanical errors are corrected. Special relativity removes that universal present. Space and time are not separate backgrounds. They form a connected geometry called space-time. Observers moving relative to one another can disagree about the duration between events, the distance separating locations, and even whether distant events occur at the same time. They do not disagree because one observer has made a mistake. They are measuring different slices of the same physical reality. The effect begins with one uncompromising rule. Every inertial observer measures light moving through vacuum at the same speed. Suppose a pulse of light travels from the floor of a spacecraft to a mirror on the ceiling and returns to someone inside the craft. The light follows a simple vertical path. If the spacecraft is moving past Earth, an observer on Earth sees the ship change position while the light is traveling. From Earth, the light follows a longer diagonal route. Both observers measure light at the same speed. For the longer route to be crossed without making light move faster, more time must pass on Earth's clock than on the moving clock. This picture is only a simplified model. Real journeys include acceleration, changing reference frames, and more complicated geometry. But it reveals why time dilation is not an arbitrary penalty imposed on fast motion. It follows from the structure required to keep the measured speed of light the same for every observer. At 10% of light speed, the difference remains modest. A traveler moving steadily at that velocity experiences slightly less time than Earth. During a journey lasting about 42 years in Earth's frame, the traveler would save only a few months. The trip to Proxima Centauri is not transformed. At half the speed of light, the difference becomes more noticeable. If Earth measures 10 years of steady travel, the spacecraft experiences about 8 years and 8 months. At 90% of light speed, 10 Earth years correspond to roughly 4 years and 4 months aboard the craft. At 99%, the traveler experiences only about 1 year and 5 months, while 10 years pass on Earth. The final fractions matter enormously. A spacecraft moving at 90% of light speed is fast, but a craft moving at 99.9% experiences a much stronger relativistic effect. Each additional step toward light speed requires more energy than the step before it, yet each step also increases the difference between Earth time and traveler time. This difference is described by the Lorentz factor, usually represented by the Greek letter gamma. Gamma begins close to 1 at low velocity. As speed approaches that of light, gamma grows without limit. If gamma equals 10, Earth may measure 10 years while the traveler experiences roughly 1, assuming a suitable period of steady motion. If gamma equals 1,000, 1,000 years outside may correspond to about 1 year aboard the ship. The traveler has not exceeded the speed of light. No local measurement shows the spacecraft racing through nearby space faster than light. Instead, the relationship among distance, duration, and simultaneity has changed. From Earth's frame, a distant star remains the expected number of light years away, and the journey still requires at least that many years for anything travelling below light speed. From the traveller's frame, the distance along the direction of motion is contracted. The star is closer. This does not mean the destination has physically been crushed or pulled toward the spacecraft. Length contraction is the distance assigned within the traveller's frame, produced by a different definition of simultaneity. Time dilation and length contraction are not two unrelated tricks. They are two descriptions of the same space-time relationship. Earth says the distance remains large while the traveller's clock accumulates less time. The traveller says the onboard clock advances normally while the distance becomes shorter. Both descriptions predict the same departure and arrival events. This transforms the title. Until now, an 80-year lifetime has meant 80 years passing on Earth. A probe travelling at 20% of light speed could cross roughly 16 light years during that interval if acceleration and braking were ignored. Even at 90%, the straight line limit remains 72 light years. Those limits apply to Earth's clock. They do not necessarily apply to the traveller's aging. A person moving close enough to light speed could experience only a few decades while hundreds, thousands, or millions of years passed outside the ship. Their personal lifetime could contain a journey far larger than the distance light covers in 80 Earth years, because far more than 80 years would pass in Earth's frame. The traveller does not gain extra speed. The traveller gains less elapsed time. If the mission must launch, explore, and report its discoveries to the same generation on Earth, then Earth's clock controls the range. Relativity provides little comfort. The people waiting at home still endure the full travel time and the full communication delay. If the mission is judged only by whether the traveller remains alive upon arrival, then the accessible map becomes radically larger. A human might cross distances that would require longer than recorded history in Earth's frame, while aging by only a small part of an ordinary lifespan. But this apparent escape from mortality carries a cost more severe than fuel. The traveller may survive. Their world does not wait. Suppose a crew leaves Earth on a relativistic journey and experiences 10 years before reaching a distant system. Depending on the speed and destination, decades, centuries, or far longer may have passed on Earth. Languages may have changed, governments, borders, institutions, and cultures may have vanished. The people who designed the ship may be ancient history. A return journey increases the separation. The crew might experience another decade, while Earth advances through another vast interval. By the time the spacecraft comes home, the planet may contain no living memory of the departure. Relativity preserves biological time by consuming historical connection. The mission has crossed not only space, but history. One human lifetime therefore produces two maps. The Earth time map remains tight. Nearby stars may become reachable with advanced propulsion, but communication, braking, and return constrain the range. The Traveller time map expands almost beyond recognition. The Milky Way, and perhaps far greater distances, begin to fit inside a few subjective decades. Both maps are correct. They answer different versions of the title. The next question is how the second map becomes possible without allowing the spacecraft to break the speed limit of the universe. The ship never breaks that limit. Instead, its motion changes how much space belongs between departure and arrival. There is less distance left to cross. That statement does not mean the traveller watches the universe visibly compress like an object being squeezed. The effect is not a distortion produced by the windows, nor a trick created by delayed light. It concerns the distance the traveller measures between locations that are moving relative to the spacecraft. To understand why, distance must first be separated from something that usually remains hidden inside it. A distance is not defined only by two positions. It also requires the positions to be measured at the same time. If someone asks for the length of a moving train, an observer standing beside the track must record where the front and back are simultaneously. Measuring the rear now and the front several seconds later would mix the train's length with its motion. For objects moving slowly, everyone agrees closely enough about what simultaneously means. The disagreement is too small to notice. Near light speed, simultaneity becomes part of the physics. Earth and the spacecraft do not divide distant events into past, present, and future in exactly the same way. Events that Earth considers simultaneous may not be simultaneous in the traveller's frame. This difference changes the measured separation between Earth and the destination. From Earth's perspective, imagine two stars separated by 10 light years. Their positions are measured at the same moment in Earth's frame. A spacecraft crossing the gap at 99% of light speed requires a little more than 10 Earth years to travel between them. The crew does not experience those same 10 years. At 99% of light speed, the Lorentz factor is a little above 7. Ignoring acceleration, the travellers experience only about 1/7 as much time as Earth measures during the cruise. Their clocks remain normal. Their speed relative to the stars remains below light speed. For both statements to remain true, the distance between the stars in the spacecraft's frame must be shorter than 10 light years. It contracts to roughly 1/7 of its Earth frame length. The travellers therefore cross a distance of about 1.4 light years at nearly the speed of light, which fits naturally into their shorter elapsed time. Neither description is more real than the other. They are measurements made from different states of motion, and both predict the same physical meetings, departure from the first star and arrival at the second. A map can provide a limited way to picture this. Imagine drawing Earth and the destination on a sheet of transparent material. The traveller does not merely move across that fixed sheet while carrying a slow clock. The traveller's state of motion changes how the sheet is divided into space and time. What Earth labels as a large spatial separation partly appears in the traveller's coordinates as a difference in the timing of distant events. The analogy must stop there. Space-time is not a physical sheet that bends or slides beneath the spacecraft. Nothing is mechanically folding the route. The useful point is only that space and time are not measured independently. Changing motion changes the way an observer assigns coordinates to both. This is why length contraction occurs only along the direction of travel. The spacecraft does not see planets compressed in every direction. A planet passing beside the ship is not transformed into a universally flattened object. Different observers measure different lengths because they disagree about which distant points are being measured at the same time. The object does not possess one absolute length that every observer must share. The same structure prevents the spacecraft from locally overtaking light. Suppose the crew switches on a lamp and sends a beam toward the front of the cabin. They measure the light moving away at the ordinary speed of light, not at the speed of light minus the spacecraft's velocity. An observer on Earth also measures that beam moving at the speed of light. Velocities near light speed do not combine through simple addition. The relativistic rule ensures that no observer sees light moving faster or slower through vacuum merely because its source is moving. The spacecraft may cross a contracted galactic distance within a few decades of personal time, but it never passes a local light beam. At every point along the journey, light still escapes ahead. That local distinction matters because phrases such as crossing 100,000 light-years in 20 years can sound like faster-than-light travel. From Earth's frame, the trip still takes slightly more than 100,000 years. From the traveler's frame, the contracted distance may fit inside decades. The ship does not complete an Earth-measured 100,000 light-year route in 20 Earth years. It completes a shorter, traveler-measured route in 20 traveler years, while an enormous amount of Earth time passes. Acceleration complicates the story, but does not rescue a universal clock. A real mission must leave Earth, increase its speed, perhaps cruise, turn around, and decelerate. During acceleration, the traveler changes reference frames. The neat description of two observers moving steadily relative to one another must be replaced by a full account of the ship's changing motion. Yet, the accumulated time can still be calculated. The clock carried aboard the spacecraft follows its own path through space-time. Earth's clock follows another. When the two are compared at departure and, if possible, reunion, they may show radically different elapsed times. This has already been confirmed on far smaller scales. Highly precise clocks moved at different velocities do not remain perfectly synchronized. Fast, unstable particles created high in Earth's atmosphere survive longer in the laboratory frame than they would without time dilation, allowing many to reach the surface. Satellite navigation systems must account for both special and general relativity to produce accurate positions. Relativity is not a decorative theory reserved for impossible starships. The extreme voyage enlarges effects that are already measured. What remains impossible with present technology is not the geometry. It is creating and sustaining the required motion. To make the distance to a remote star contract dramatically, the spacecraft must reach a velocity so close to light speed that the difference between 99% and 99.9% becomes physically decisive. At 90% of light speed, gamma is about 2.3. At 99%, it is about 7.1. At 99.9%, it is about 22.4. At 99.999%, it is about 224. Add one more 9, 99.9999%, and it rises beyond 700. Each added series of 9s reduces the traveler's elapsed time, but gaining those 9s demands an increasingly severe rise in energy. There is no final engine setting marked almost light speed. There is an asymptote. The spacecraft can approach light speed more closely, but an object with mass cannot reach it. As velocity increases, additional energy produces smaller increases in speed, while continuing to increase momentum and the relativistic energy of the craft. That limitation does not prevent extraordinary subjective journeys. It determines their price. Consider a craft capable of maintaining an acceleration equal to gravity on Earth. The crew would feel a steady force pressing them toward the floor. During the first half of the journey, the ship accelerates. At the midpoint, it turns around. For the remaining half, it accelerates in the opposite direction, which slows it relative to the destination. Inside, the crew might experience something resembling ordinary weight. Outside, the ship approaches light speed more and more closely. The longer the journey continues, the more severe the separation becomes between Earth time and traveler time. The craft never reaches light speed, but its gamma factor can grow large enough for enormous external distances to contract into a manageable subjective voyage. A nearby star requires only a few years aboard such an idealized ship. A destination hundreds of light years away may require less than a decade of traveler time. the center of the Milky Way begins to look reachable within a human career. Even the far side of the galaxy can fit inside a human lifetime, measured aboard the craft. This does not mean the galaxy has become small for everyone. Earth still waits, tens of thousands of years. The stars continue evolving. Civilizations have time to rise and disappear. The travelers cross a contracted distance while moving into a future that grows more remote with every second of their own lives. The 80-year clock has therefore become a deeply personal instrument. It no longer measures how long the universe waits. It measures how much of the traveler remains when the destination finally arrives. And under the ideal conditions permitted by relativity, that clock can carry a human being much farther than the nearest stars. It may be long enough to cross the Milky Way. It may be long enough to cross the Milky Way. Take the idealized spacecraft we have already imagined. It can accelerate continuously at one Earth gravity. For the first half of the journey, its engines push it toward the destination. At the midpoint, the ship turns around. The same acceleration then points backward, removing velocity until the craft arrives at rest relative to its target. Inside the cabin, the crew feels a steady downward force similar to standing on Earth. Their clocks move normally. Their meals, sleep, thoughts, and aging proceed without any sensation that time has changed. Outside, the result becomes increasingly extreme. A journey to Proxima Centauri, about 4.24 light-years away, would take roughly 3.5 years for the travelers under this perfect acceleration and deceleration profile. Nearly 6 years would pass in the frame shared by Earth and the destination. The ship would approach about 95% of light speed near the midpoint before slowing. That alone is far beyond any propulsion system humanity possesses, yet relativity permits it. Nothing in the calculation requires the spacecraft to exceed light speed. Extend the destination to 100 light-years. The people aboard would experience about 9 years. Earth would wait a little more than 100 years. Near the midpoint, the ship would move so close to light speed that its velocity would differ from light by only a tiny fraction. Move the target to 1,000 light-years. The traveler's journey grows to roughly 13.5 years. Outside the craft, a little more than 1,000 years pass. The distance has increased by a factor of 10, but the travelers have added only about 4.5 years to their voyage. That is the pattern that makes relativistic travel so difficult to imagine. Once the ship spends most of its journey extremely close to light speed, increasing the destination distance does not increase the crew's elapsed time in direct proportion. The additional external distance becomes increasingly contracted in their frame. Enormous spans of the galaxy can be added while the onboard clock advances by only a few more years. The center of the Milky Way lies roughly 26,000 light-years from Earth. Under the same impossible one-gravity assumption, the travelers could reach the galactic center within about 20 years of personal time. More than 26,000 years would pass outside. The craft would arrive in a region crowded with stars, gas, dust, stellar remnants, and the 4 million solar mass black hole known as Sagittarius A star. But Earth would no longer belong to the historical period remembered by the crew. 26,000 years separate us from people who lived before agriculture, cities, writing, or permanent states. A similar interval would separate the travelers from the civilization that launched them. Crossing the full diameter of the Milky Way produces the clearest version of the trade. For a destination 100,000 light-years away, the travelers would experience about 22 years and 4 months. In Earth's frame, the journey would require a little more than 100,000 years. A person could depart while young and arrive before middle age. The light that left Earth at departure would still be moving through the galaxy behind the ship. Any message transmitted after arrival would need another 100,000 years to return. The mission could fit inside a human life. Its conversation with home could not fit inside a civilization. A crew might personally visit a distant part of the Milky Way. They could slow near a star, examine planets, collect samples, and spend years investigating. their subjective lifetime might permit all of it. But none of that knowledge would return to the Earth they knew. Even if the crew immediately transmitted its results, the message would travel at light speed while history continued. By the time the signal reached the solar system, the original languages, institutions, and perhaps the human species itself might no longer exist. The travelers could explore for themselves. They could not explore on behalf of their own generation. A return journey deepens the separation. The crew might cross the galaxy in a little over 22 years, remain for several years, and then spend another 22 returning. They could reach the solar system while still within an ordinary lifespan. Earth would have advanced by roughly 200,000 years. The planet might remain habitable, human descendants might still be present, yet the society waiting would be more distant from the crew than modern civilization is from the earliest members of our species. The ship would not return home in the usual meaning of the word. It would return to the same location in space. The idealized journey can be extended beyond the Milky Way. The Andromeda galaxy lies about 2.5 million light-years away. Under continuous one-gravity acceleration for half the journey and equal deceleration for the second half, the crew would experience roughly 28.5 years. Outside, about 2.5 million years would pass. A traveler could, according to special relativity, leave Earth, cross intergalactic space, and arrive in another major galaxy before growing old. The journey would not feel brief. 28 years remains a large part of a human life. The crew would watch decades pass inside the ship. Children might become adults. Adults might age into their final years. But the external universe would advance through a duration longer than the entire existence of our species in its present form. Earth's continents would move. Climate would change repeatedly. Species would emerge and disappear. The night sky seen from the solar system would alter as nearby stars followed their paths through the galaxy. The traveler's personal future would become the deep future of everything they left behind. Relativity has not granted immortality. It has created a one-way exchange. The crew preserves its own time by surrendering synchronization with the rest of the universe. The same exchange prevents this from becoming an easy tour of the cosmos. A traveler cannot visit Andromeda, return to report what was found, and continue life in the century that launched the mission. A return could still fit inside the traveler's biological lifetime under sufficiently extreme conditions, but roughly 5 million years would pass outside. The people who received the report would not be the people who requested it. Perhaps no one would be waiting. Perhaps the solar system would contain a civilization advanced enough to regard the returning ship as an artifact from prehistory. Perhaps Earth would no longer be inhabited. The physics provides the elapsed times. It does not guarantee a homecoming. Every figure so far also rests on assumptions that become more unrealistic as the destination expands. The engines never fail. They produce one Earth gravity for years or decades. The spacecraft carries or receives enough energy to continue accelerating. Waste heat escapes. The crew survives radiation. Dust does not destroy the vehicle. Navigation remains precise. The ship turns at the correct midpoint and decelerates flawlessly. Nothing in known engineering comes close to supporting all of those conditions. The thought experiment is not a mission proposal. It reveals the boundary between what relativity permits and what technology can perform. Within that mathematical boundary, one lifetime can contain Proxima Centauri, the galactic center, the far side of the Milky Way, and even Andromeda. Within the practical boundary of any propulsion system humanity has built, none of them is remotely accessible. The gap between those two maps is where the remaining problem lives. Space itself does not forbid the traveler from crossing the galaxy before growing old. The universe demands payment in energy, protection, and the irreversible loss of the time left behind. The first payment is energy. A spacecraft does not become difficult to accelerate only at the speed of light. The difficulty begins much earlier, then grows more severe with every additional fraction of that speed. At low velocities, kinetic energy can be estimated with the familiar expression 1/2 of mass multiplied by velocity squared. Doubling the speed requires 4 times the kinetic energy. That alone is unforgiving. Near light speed, the classical equation stops being accurate. Relativistic kinetic energy depends on the same Lorentz factor that produces time dilation and length contraction. As velocity rises, the spacecraft's momentum and total energy increase ever more sharply. Its rest mass does not need to become larger. The energy required to produce each additional increase in speed simply grows without limit as the craft approaches light speed. No final push carries a massive object across the boundary. Reaching light speed would require infinite energy. Even speeds far below that limit are immense engineering events. Consider a spacecraft with a total mass of 1,000 kilograms, less than many ordinary cars and far too small to support a human crew. Accelerating that single ton to 10% of light speed requires about 4.5 times 10 to the 17th joules of kinetic energy. That is equivalent to roughly 108 megatons of TNT, placed entirely into the craft's forward motion. This is the minimum physical energy of the moving vehicle. It does not include energy wasted by the propulsion system. It does not include the mass of an engine. It does not include propellant, shielding, communications equipment, scientific instruments, or power systems. It does not include the energy required to slow down. A probe traveling at 20% of light speed carries more than 4 times as much kinetic energy as the same probe at 10%. At 90%, the increase is far more severe. The spacecraft's speed may grow by a modest factor while its energy demand grows by orders of magnitude. This is why near-light speed travel is not ordinary rocketry performed for a longer time. The final increments of velocity become disproportionately expensive, even though they are the increments that produce the strongest time dilation. Relativity offers its greatest subjective distances precisely where the energy problem becomes most severe. The one-gravity journey across the Milky Way illustrates the conflict. Inside the thought experiment, the engines produce a comfortable acceleration year after year. The travelers feel weight. The external distance contracts. The onboard clock reaches the far side of the galaxy after only a few decades. But acceleration is not merely a force that remains switched on. It is a continuous transfer of energy and momentum. As the ship moves faster, maintaining the same felt acceleration requires the propulsion system to continue increasing the craft's relativistic momentum. The engine must operate for years without losing thrust, overheating, exhausting its energy supply, or destroying itself. The crewed vehicle would not weigh 1 ton. A habitat capable of supporting people for decades would likely require substantial shielding, life support machinery, water, structural material, radiators, replacement parts, power equipment, and propulsion hardware. Every kilogram of that structure enters the energy equation. If the craft relies on onboard reaction mass, some material must be expelled backward to push the vehicle forward. High exhaust velocity reduces the amount required, but producing high exhaust velocity demands energy. The propulsion system must turn stored energy into an extremely fast and carefully directed exhaust while avoiding destructive losses. Chemical reactions release too little energy per unit mass for relativistic interstellar travel. Nuclear fission contains far more. Fusion could release a larger fraction of the fuel's mass as useful energy. Matter-antimatter annihilation offers the theoretical possibility of converting still more rest mass into energy, but producing, storing, controlling, and directing macroscopic quantities of antimatter lies far beyond demonstrated propulsion technology. Even an ideal fuel does not create an ideal engine. Energy released in random directions does not efficiently accelerate a spacecraft. The propulsion system must channel that energy into exhaust moving backward. Any portion that becomes unwanted heat, radiation, turbulence, or unusable particles does not contribute fully to forward motion. Efficiency therefore controls 2 penalties at once. Poor efficiency requires more fuel. Poor efficiency also creates more waste heat. Heat is easy to underestimate in space because space is cold, but cold surroundings do not automatically cool a spacecraft. On Earth, hot machinery can transfer energy into moving air or circulating water. In vacuum, a spacecraft cannot rely on surrounding matter. It must eventually radiate unwanted heat away as electromagnetic energy. That requires surface area. Radiators transport heat from engines, reactors, electronics, and living spaces to broad external panels, which emit infrared radiation into space. More waste heat may require larger radiators or higher operating temperatures. Larger radiators add mass, structure, pumps, fluid lines, and exposed surfaces vulnerable to failure. An interstellar engine operating continuously at extraordinary power would magnify that problem. The spacecraft cannot convert all supplied energy into motion. A real machine generates heat through electrical resistance, imperfect reactions, friction inside pumps, radiation absorbed by structures, and inefficiencies in power conversion. If the engine produces more heat than the radiators can remove, temperature rises. Electronics fail, materials weaken, coolants boil or decompose. The crew's habitat becomes unlivable. The ship may possess enough total energy for the voyage and still be unable to use it quickly enough without destroying itself. This separates energy from power. Energy is the total capacity to perform the journey. Power is the rate at which that energy can be released, controlled, converted, and rejected. A propulsion system with an enormous energy supply but low power might require centuries to accelerate the spacecraft. A system with extreme power might provide rapid acceleration while producing heat and mechanical stress that no structure can survive. The one-gravity thought experiment requires both. The energy supply must remain vast. The power must remain high for years. The radiators must remove the losses. The structure must survive continuous thrust. The propulsion system must remain reliable through billions of seconds of operation. Then, at the midpoint, the process must be repeated in reverse. Deceleration does not refund the kinetic energy automatically. A braking engine must transfer the ship's forward momentum somewhere else. It may expel reaction mass, interact with a magnetic field, push against stellar light, or transfer energy into another physical system. Whatever method is used, the motion must be removed without destroying the vehicle. For a self-powered mission, reaching the target and stopping there demands at least two enormous energy transformations, one to gain the velocity and another to lose it. A return journey adds two more. The causal chain closes around the spacecraft. More speed requires more kinetic energy. More energy requires a larger propulsion system. A larger propulsion system creates more waste heat. More heat requires larger radiators. The radiators add mass. That mass demands still more energy. The engine grows because the ship is heavy, and the ship grows heavier because the engine must survive being powerful. Beamed propulsion tries to reduce one part of this burden by leaving the energy source behind. A powerful array near the solar system could direct light toward a sail, allowing the probe to accelerate without carrying its main power plant or most of its reaction mass. The beam, however, must remain accurately focused across an increasing distance. The sail must survive intense illumination. The infrastructure near the sun must generate and control extraordinary power. The spacecraft still needs protection, navigation, communication, and a method of braking at the destination. Moving the engine away from the probe does not remove the energy requirement. It changes where the requirement is paid. That is the true energy wall. Physics does not forbid a spacecraft from approaching light speed. It makes every useful kilogram increasingly expensive to accelerate, increasingly difficult to protect, and increasingly difficult to stop. Relativity can shorten the traveler's journey. It does not reduce the energy carried by the moving ship in Earth's frame. And even if a civilization learned to produce that energy, convert it efficiently, reject the heat, and keep the engines running for decades, the path ahead would not be empty. At relativistic speed, emptiness begins to strike back. Interstellar space contains far less matter than the best vacuums naturally found on Earth. But it is not perfectly empty. Gas drifts between the stars. Microscopic grains of carbon, silicates, ice, and metals move through the same darkness. Cosmic rays arrive from distant energetic events. Photons fill the sky at every wavelength. At Voyager's speed, these particles are scientific subjects. At a meaningful fraction of light speed, they become projectiles. The danger does not come from the particles suddenly growing larger. It comes from the relative velocity between them and the spacecraft. From the ship's frame, material that appears almost stationary within the galaxy approaches from directly ahead at the speed of the vehicle. A hydrogen atom is extremely small. At 10% of light speed, it carries enough energy in the spacecraft's frame to behave more like ionizing radiation than an ordinary gas particle. The ship does not feel a gentle wind. It encounters a stream of individual impacts energetic enough to damage molecular structures, disturb electronics, and gradually weaken exposed material. The gas is sparse, but the journey is long. A spacecraft crossing 1 light-year sweeps through a corridor almost 10 trillion kilometers in length. Every square meter of its forward surface encounters the particles occupying that immense volume. Most impacts are individually tiny. Their cumulative effect may not be. The front of the spacecraft becomes the place where the quiet interstellar medium is converted into heat, radiation, electrical charge, and material damage. At higher speeds, incoming particles can penetrate surfaces, displace atoms inside shielding, and produce secondary showers of fragments. A shield does not merely stop the original particle. The collision can create additional particles moving through the structure. The problem becomes more severe when dust is added. Interstellar grains vary greatly in size. Many are far smaller than a grain of sand. Some may be only fractions of a micrometer across. Their smallness makes them difficult to detect from a useful distance, but it does not make them harmless. At 10% of light speed, a particle weighing 1 milligram carries kinetic energy on the order of hundreds of megajoules, comparable to the explosive energy of more than 100 kilograms of TNT. A milligram is not a boulder. It is smaller than many visible grains of sand. The exact risk depends on how frequently grains of that size occur along a particular route, and that distribution remains uncertain. But a single direct strike could vaporize both the grain and part of the spacecraft's surface. The expanding plasma might damage neighboring structures. A larger particle could punch through shielding or release enough energy to threaten the entire vehicle. The spacecraft cannot simply turn aside at the final moment. A particle visible 1 second ahead at 20% of light speed is already 60,000 kilometers away. But detecting a dark, microscopic object at that range would be extraordinarily difficult. At higher velocities, the required response becomes even faster. The craft also possesses enormous momentum. A sudden, evasive maneuver strong enough to avoid a tiny grain may be impossible for a large ship, especially when the particle's position and trajectory are not known precisely. Protection must therefore be built into the vehicle before launch. One possible defense is a thick sacrificial shield at the front. Layers of material absorb impact, break up incoming grains, and spread their energy before it reaches the habitat or instruments. A Whipple shield, used on present spacecraft against orbital debris and micrometeoroids, places a thin outer layer ahead of the main wall. An impact vaporizes or fragments the incoming particle, allowing the resulting cloud to spread before striking the deeper structure. An interstellar version would face far greater energies. Multiple layers might gradually disperse the impact. Water, ice, carbon-based materials, or other low atomic mass substances could help absorb particles while producing less damaging secondary radiation than some heavy metals. A crewed ship already needs water. Placing tanks around the forward habitat could allow one mass to perform several functions: drinking supply, radiation protection, thermal storage, and impact shielding. But every shield has mass. Every kilogram added to the front must be accelerated to interstellar speed. The propulsion system must then slow that mass at the destination. If the shield is gradually eroded, the spacecraft must begin with enough material to survive the full journey. A mission crossing the Milky Way rather than traveling to the nearest star encounters matter across a vastly longer path. Relativity shortens the distance measured by the travelers. It does not allow them to ignore the material they encounter between departure and arrival. The exact number of collisions depends on the density and composition of the route. Interstellar space is not uniform. A path may pass through relatively thin regions, denser clouds, dust structures, or environments altered by nearby stars. Mission planners would need a three-dimensional map far more detailed than anything currently available. The best trajectory might not be the geometrically shortest one. A longer route through cleaner space could be safer than a direct line through a dense cloud. Navigation becomes a form of weather forecasting conducted across light years. Active protection has also been proposed. A spacecraft might release a cloud of fine material ahead of itself, allowing distant collisions to occur before the particles reach the main vehicle. Lasers could attempt to detect heat, vaporize or deflect larger grains. Magnetic or electric fields might redirect charged particles. Each method solves only part of the threat. Neutral dust does not respond easily to a magnetic field until it is ionized. A laser requires power, precision, and enough warning distance. A forward cloud disperses and must be continually replenished. Strong electromagnetic systems add mass and generate heat. A defensive system may consume a significant portion of the spacecraft's total energy. The faster the ship moves, the farther ahead it must control its environment. Incoming light changes as well. Photons arriving from the direction of travel are blue-shifted. Their wavelengths become shorter and their energy increases in the ship's frame. Visible light can shift toward ultraviolet. Higher energy radiation can become more dangerous. Light arriving from behind is redshifted and weakened. At extreme velocity, the peaceful sky becomes concentrated. Stars ahead appear displaced toward the forward direction by relativistic aberration. Radiation that was spread across a wide region of the sky is compressed into a narrower cone. The spacecraft does not see the universe as a calm sphere of familiar stars. Much of the external light gathers toward the path ahead and shifts into unfamiliar wavelengths. The forward shield must therefore confront more than dust. It faces gas, radiation, energetic particles, and concentrated light. Behind that shield, the crew still needs to observe and navigate. Instruments require an opening, sensor, or indirect view of the space ahead. Every aperture becomes a possible weakness. A telescope, protected behind thick material, cannot see through the shield. A telescope placed outside the shield is exposed. Engineers may need mirrors, replaceable sensors, distributed probes, or instruments positioned far from the main habitat. Small scout vehicles could travel ahead and send warnings backward, but the warning cannot move faster than light. At relativistic speeds, the time between detection and impact may remain short. A crewed ship must carry a working environment inside an armored projectile. The armor increases mass. The mass increases energy demand. The greater energy demand enlarges the propulsion and cooling systems. Those systems add more mass. The effort to protect the spacecraft therefore strengthens the very energy wall that made the journey difficult. This feedback may determine the practical speed limit long before relativity imposes its absolute one. Physics permits a massive craft to approach light speed. Engineering may discover that surviving interstellar matter limits a useful vehicle to a much lower fraction. A tiny probe can accept risk. Thousands might be launched in the hope that a few survive. A human crew cannot be treated as a disposable swarm. The voyage must endure every significant impact, every radiation event, every equipment failure, and every uncertain region along the route. A single unobserved grain cannot be allowed to end decades of travel. The emptiness between stars is therefore not the absence of a problem. It is a problem distributed thinly across an enormous distance. the ship may survive the laws of relativity and still be defeated by matter too small to see. Yet even a perfectly protected ship would face a boundary no shield could alter. Some galaxies are not simply far away. The expansion of space-time is carrying them beyond any journey that can ever begin here. This creates the largest difference yet between seeing a destination and reaching it. The observable universe is not a sphere of objects waiting at fixed positions. It is a record made from light that has been traveling toward us while the universe expanded. When astronomers observe a galaxy billions of light years away, they do not see it as it exists now. They see the galaxy as it was when the light began its journey. During the time that light traveled, the space between the galaxy and the Milky Way continued to grow. The galaxy's present distance can therefore be much larger than the light travel time might suggest. The universe is about 13.8 billion years old. In the standard cosmological model, the matter whose oldest light reaches us today is now estimated to lie at a present co-moving distance of roughly 46 billion light years. This does not mean light travelled faster than light for 46 billion years. It means the distance to the matter that emitted the oldest observable light increased while that light was moving toward us. Expansion changes the scale beneath the journey. This is not ordinary motion through space. A distant galaxy can recede from us because the space between large cosmic structures is expanding. Nearby stars, planetary systems, and gravitationally bound galaxies do not expand internally in the same way. Gravity and other forces hold them together. Across enormous distances, however, the accumulated expansion becomes dominant. A galaxy sufficiently far away can recede from us faster than light without violating special relativity. The galaxy is not locally racing through nearby space faster than a beam of light beside it. The distance between us and the galaxy is growing because the intervening space-time is expanding. The local speed limit remains intact. No spacecraft passes a neighboring light beam. No message outruns light through its immediate surroundings. But the total separation between extremely distant regions can increase faster than light could cross the growing distance. That distinction creates three different cosmic maps. The first contains what is observable. We can see regions whose light has had enough time to reach us since the early universe became transparent. Everything beyond that observable boundary is hidden. Not necessarily because nothing exists there, but because no information from it has reached Earth. The observable universe may be only part of a much larger whole. The full universe could be vastly larger. It could even be infinite. Observation alone cannot settle the question. The second map contains what can still be influenced. Imagine transmitting a perfect laser signal from Earth today. The signal moves locally at the speed of light. No spacecraft could travel faster. Yet the signal does not automatically reach every galaxy currently visible in our telescopes. Under the standard cosmological model, if accelerated expansion continues broadly as expected, some galaxies are so distant that a signal sent now will never arrive. The space remaining ahead grows in such a way that the route can never be completed. This boundary is called a cosmic event horizon. It separates events that can still exchange information with us from events that will remain permanently outside our future causal reach. The word horizon is appropriate because the boundary is not a wall. Nothing marks it with a visible surface. A spacecraft would not strike it. Instead, it describes a limit in space-time. A signal emitted from one side can influence us. A signal emitted from sufficiently far beyond it cannot, even given unlimited time. The conclusion is strongly supported within the standard model, but it inherits uncertainty about the long-term nature of dark energy. If the future expansion history differs substantially from the present model, the exact causal boundary could differ as well. The third map contains what a spacecraft can reach. Every reachable destination must lie within the region a light signal can influence. A massive spacecraft moves below light speed and therefore occupies a smaller set of possible paths. Every reachable destination is influenceable, but not everything observable remains influenceable today. There are galaxies whose ancient light is reaching us now, even though we can never send a message that reaches their current or future inhabitants under the standard expansion history. We see their past. We cannot enter their future. This sounds contradictory only because vision feels immediate. When a galaxy appears in a telescope, it seems present, as though the image confirms that the object remains available somewhere ahead. The image is delayed evidence. Its photons may have begun traveling before Earth existed. They reveal what occurred at the source long ago, when the galaxy was closer in the relevant cosmological sense, and the path toward us had a different expansion history. New light emitted by that same galaxy today may never arrive. The galaxy remains visible through its old messages, while becoming unreachable through any new exchange. Over immense future time, distant galaxies outside our gravitationally bound neighborhood will appear increasingly redshifted. Their light will be stretched toward longer wavelengths and reduced in energy. Their observed processes will seem to slow. Eventually, many will fade beyond practical detection. Future observers in the Milky Way may see a much emptier universe than we do. The local group, including the Milky Way, Andromeda, and many smaller galaxies, is gravitationally bound. Its members will not be carried apart by cosmic expansion in the same way as remote galaxies. The Milky Way and Andromeda are expected to interact and merge over cosmic time. Beyond the bound local region, however, expansion increasingly controls the future separation. This places an absolute limit above every engineering limit we have encountered. A better engine can improve acceleration. More energy can increase speed. Stronger shielding can protect the ship. A more reliable habitat can extend survival. Relativistic time dilation can preserve the traveler's personal lifetime while vast ages pass outside. None of these allows the spacecraft to escape its future light cone. The path of a light signal sent today forms the outer boundary of what any slower, massive spacecraft could possibly influence. If light cannot reach a destination, neither can the ship. Time dilation does not change this. A traveler may experience only a few decades while crossing millions or even billions of light years that remain causally accessible. Their personal clock can become remarkably short compared with the external journey. But a contracted distance exists only for a route that space-time still permits them to complete. Relativity can compress the traveler's measurement of a reachable journey. It cannot convert a causally disconnected region into a reachable destination. Waiting can make the map smaller. A civilization that delays an intergalactic launch for millions or billions of years may lose access to destinations that are reachable today. The expansion of the universe continues while technology develops. This is unlike the journey to Alpha Centauri. Proxima remains gravitationally associated with the Milky Way and is not being removed by cosmic expansion. Waiting may change its stellar activity or planetary conditions, but it does not place the star beyond a cosmological event horizon. Remote galaxies belong to another category. Their accessibility can expire. The universe therefore contains places that are visible but not visitable, known in outline but unavailable to experiment, present in our sky but absent from every possible future journey. No amount of patience solves that boundary. Patience is the reason the boundary becomes final. The universe available to our eyes is larger than the universe available to our engines. Yet observation is not a lesser form of contact. A telescope can receive light from distances no traveler could cross. Spectra can reveal the composition of stars that no spacecraft will approach. Gravitational waves can report collisions that occurred before Earth formed. Ancient photons can carry evidence from regions already disappearing beyond our future reach. We may never touch those places. Still, they can change what we understand. The final question is therefore no longer simply how much of the universe a lifetime can explore. It is what we are willing to sacrifice in order to make the explored universe larger. The clock does not offer one destination. It offers 3 different sacrifices. Keep the people waiting on Earth, and the reachable universe remains a small neighborhood of nearby stars. A Voyager-like machine covers about 287 AU in 80 years, roughly 0.0045 light-year. A craft moving at 10% of light speed can draw an ideal 8 light-year line, but if its first data must return to Earth before the clock reaches 80, the farthest destination falls to about 7.3 light-years. At 20%, the ideal line reaches 16 light-years, while the destination and signal limit falls to about 13.3. Accelerate, braking, time spent observing, and any attempt to return make the honest range smaller again. This first choice preserves connection. The people who watch the launch may still receive the discovery. The price is distance. Keep the traveler young, and the map opens. Under idealized one-gravity acceleration, Proxima Centauri fits inside about 3.5 traveler years, 100 light-years fits inside about 9, the center of the galaxy fits inside about 20, the full Milky Way fits inside a little more than 22, Andromeda fits inside less than 29. This second choice preserves the body of the explorer. The price is history. The Milky Way crossing consumes more than 100,000 years outside the ship. Andromeda consumes about 2.5 million. A return multiplies the separation. The traveller may reach the destination before old age and still lose every person, institution, language, and remembered world that made the departure meaningful. Then there is the third choice. Keep the traveller on Earth. Do not cross the distance at all. Allow light, particles, and gravitational waves to complete the journey instead. A telescope can collect photons that began travelling before the sun existed. A spectrum can reveal the chemistry of a star no machine will visit. The motion of a planet can be detected through the dimming of a distant sun. The collision of black holes can send a change through space-time itself, carrying news across the cosmos until an instrument on Earth moves by less than the width of a proton. This choice preserves neither physical arrival nor personal adventure. It preserves access to evidence. The physically explored universe remains small. The intellectually explored universe becomes enormous. These are not competing answers in which one must be declared correct. They reveal that exploration has always contained more than movement. A sailor explores by arriving. A probe explores by measuring. A telescope explores by receiving. A theory explores by connecting evidence to mechanisms that no person can watch directly. Human beings have already examined the atmospheres of worlds they have never touched. They have measured the chemical composition of stars that will never receive a probe. They have detected black hole collisions across immense distances and reconstructed the early universe from ancient radiation. One person standing on Earth can spend a lifetime exploring evidence that has crossed billions of years. No spacecraft is required to travel that distance because the universe has already delivered the information. The mature answer to the title is therefore not one number. With demonstrated technology, a lifetime carries a machine hundreds of astronomical units. With advanced probes, it may carry our instruments to the nearest stars. With deep exploration, braking and communication reduce that range. With idealized relativity, it may carry a traveler across the galaxy or beyond, but only by abandoning the time that launched them. Through observation, one lifetime can examine evidence from across most of visible cosmic history without physically crossing the distance at all. The 80-year clock reaches its final minute. Outside the spacecraft, the sun may still be the brightest object in the sky, or it may have become one star among billions, or the galaxy itself may lie behind the traveller as a distant spiral of light. The distance crossed depends on the machine. The time passed depends on the observer. What remains connected depends on the mission. And what has truly been explored depends on whether exploration requires presence, understanding, communication, or return. The final seconds disappear. The traveller has gone farther than any human being before them, perhaps farther than anyone left on Earth could imagine. Yet almost all of the universe remains untouched, and the small part reached has demanded a price measured not only in energy or years, but in separation from everything that made the journey meaningful. A lifetime may be long enough to cross the darkness, but not long enough to keep the universe on both sides of the journey unchanged.